Y6 capacitance. We have parallel plate capacitor here, plus sigma and minus sigma, Z equals 0, Z equals D. According to Gauss' law, electric field outside is 0, and between the two plates is sigma over epsilon 0. Any sigma will give sigma over 2 epsilon 0, sigma over 2 epsilon 0. If it is negatively charged, it is toward the plate. And according to superposition principle, sum of these two will produce the electric field between the two plates. And this is the parallel plate capacitor. Electrostatic potential, this is a positively charged plate. So potential is the largest in here, smallest in there. Here we have set V0, V equal V0 at the negatively charged. This should be positive. Okay, at Z equals D. No, Z equals 0, it should be replaced with a plus and positive. Sorry about that. I have to write it down. 1B plus sigma at Z equals 0. Okay, so here this is V0, and the positively charged plate, wait a second. No, this is different problem. This problem, there's nothing wrong. We have minus sigma here. This is a plus the sigma is here. Okay, so potential is increasing. This is a minimum value. And at this plate, it is stated that V equals V0. So everywhere on the left-hand side is V0 and increases from V0 from 0 to D like that. And if we substitute Z equals D, this value is this. And then right-hand side is again frozen. Constant. Okay, there's nothing wrong. Okay, constant electric field is 0. V equals constant, electric field is 0. And electric field is in this direction because minus gradient equals minus Z derivative and E3 hat. Okay, that's it. The potential difference between the two charged plates is E times D. This is electric field between the two plates, and sigma equals Q over A. Let's see. Sigma is here. We multiply A in the numerator denominator. They cancel, so this is identical. And sigma A is a charge Q. From this expression, charge Q is something multiplied by V. And the formula Q equals CV states that this coefficient is the capacitance of the parallel plate capacitor. So it is proportional to the area and then it is inversely proportional to the distance between the two plates. Next, we have a coaxial cable. Inner radius is A and outer radius is B. And inside is a positively charged. And here the charge over length. This is the length. And inside is a positive, outside is a negative. So electric field diverges from inside to outside. However, here in inner radius, smaller than the inner radius and greater than the outer radius, electric field vanishes. E is absolutely zero. And E equals 0 means V equals a constant. Remember, the electric field vanishes in here and outside. Gauss law can be applied to electric field. This is identical to the case of just a straight line charge distribution. Okay, so this is similar to Gauss, similar to Shell theorem. For a cylindrical symmetry, it is just like the case of infinite wire uniformly charged with charge density lambda, that is a Q over L. Okay, and we remember there's a factor of 2 instead of 4. To have the electric field in here, we have the potential. And the potential has a reference value, so it can be added. Any constant C can be added. To simplify our analysis, usually we set at infinite point far away from the coaxial cable, rho goes to infinity, we take potential goes to 0. In that case, because outside the coaxial cable in here and at the infinite, these are 2 points, we have a constant potential. So because infinite is 0, so this is 0 from just outside the outer radius. And inside, we have this electric field. This electric field can only be produced by this log dependence, because we have to find E rho and rho derivative, partial derivative. Only if we have log 1 over rho, we have this negative sign cancels, so we have log 1 over rho. However, this B has been chosen. If I substitute rho equals B, it should be 0. Because log 1 equals 0, I can put this constant as a B so that it can reproduce the value 0 at rho is greater than B. This is because the potential is a continuous function, while the electric field has a discontinuity at the boundary. Okay? And then what can I do to fix this value? Because we have fixed this value, I can substitute rho equals A, and inside the inner radius, electric field vanishes, so potential should be a constant. So this one is identical to the value of this region at rho equals A. Because of this, we can determine the potential difference between rho equals B and rho equals A. That difference is nothing but this amount. So using this one, I can write it down in the form of Q equals CV, and Q equals CV states that the capacitance of this coaxial cable is like that. We have a carbon copy of the same problem. Instead, we have two spheres of inner radius A and outer radius B, and yellow surface is a field point. Sure, Gauss' law states that inside this inner sphere and outside of outer sphere, both of them do not have electric field. So in both the regions, V equals a constant. Okay. And in here we have charge Q, in here we have minus charge Q. So between these two spheres, we know how to compute the electric field. It is just like a point charge Q is placed at here because of the shell theorem. This contribution does not appear between the two spheres. So this is the electric field that we have, and potential should be vanishing as R goes to infinity. So outside it must have a zero. Between the two, the R dependence of the potential should be 4 pi epsilon 1 over R. And we need some constant. This constant is determined by fixing the value, substituting this value at R equals the B. Okay, so this is the way. If we substitute R equals B, same thing, subtraction, it is 0. Okay, this is the value. What can I do for this one? This value is frozen. Inside is frozen as a constant. So at the boundary, I substitute R equals A to find this one. And the difference of these two is the potential difference between the inner and outer sphere. Therefore, this V is determined like that. From this, I apply Q equals CV, and the coefficient C, capacitance, is determined like that. We have a parallel plate capacitor, completely discharged, and I add more charges to have a completely charged state. We have a state Q and minus Q. In this case, there is a potential difference V. And then I bring plus Q from here. This is a plus dq and minus dq equals 0. I bring this plus dq to here. Then it becomes q plus dq, and this side is a minus q minus dq. And finally, I approach capital Q and minus Q. So let's find the electric field. This is what we have derived already. What should I do to bring plus dq from to there? The work is the potential difference multiplied by charge. Potential difference is given in here. I copy this result, and we have Q. V is proportional to Q. And Q dq is just the differential of 1/2 Q squared. And we remember, what is that? This is just 1 over C, capacitance. And this one can be integrated to find the total work from completely discharged state to fully discharged state to Q. And the final result is because the Q equals CV, it is a Q squared over 2C or 1/2 CV squared. So we have electric field between the positive plate and negatively charged plate. The electric field is inside the plate and there is no electric field outside. We remember what we have done? This work to charge the capacitor from completely discharged state to a charged state of finite Q is 1/2 CV squared over Q squared over 2C. And this is what we have done. However, it can be expressed in terms of the electric field. And electric field relation is given in here. Potential and electric field that related like that. Because of this, express C in terms of area and distance between the two plates, and we rewrite the potential energy, electrostatic potential energy of the parallel plates in terms of this one, this is C, 1 over C is here, charge Q is here. Okay. And then we rewrite this one with sigma, that is a charge density, QA. All right, what is that? This is a sigma over epsilon 0. What is the sigma over epsilon 0? That is the strength of the electric field. So we pull this electric field square in here, and D times A is the volume inside the parallel plate capacitor, and we have a coefficient epsilon 0. Therefore, this electrostatic potential energy is identical to the volume integral of 1/2 epsilon 0 electric field square. We say, because this volume integral is the energy, we say this is the energy density of the electric field. Number 6, you can follow number 6 and 7. You can follow these calculation 6 and 7. This is just application of the how to compute the electric field energy of volume integral, and using this you can find the electric field 1/2 epsilon 0 E squared, and this parallel plate capacitor has a constant electric field that is a sigma over epsilon 0, and you carry out the volume integral, compare these two, and actually this is electrostatic energy. The difference of the electrostatic energy will give the required work done by you to save more energy or less energy. Okay? Next, consider uniform charge distribution of charge Q on a spherical surface of radius r centered at the origin. Same situation, we know very well about this. The potential outside the shell is just like the same as the point charge Q placed at the origin. Inside, the electric field vanishes. Therefore, the potential inside is the same as the value at the boundary. So we substitute capital R to small r. And actually, the potential does not contribute to the electric field energy. The electric field energy should be evaluated as a volume integral. And for the case of potential, we have to integrate over charge. The work required to bring dq from r goes to infinity, because this is a single, there is a no, remember, we have two spares. We have a q and minus q, then bring in here, it is dq minus dq. Bring this dq in here, then you will arrive at q plus dq and minus q minus dq. In this problem, we have inner radius A and outer radius B. And this problem is the same as the previous problem when we take B goes to infinity. B goes to infinity. So I hope you repeat the calculation by substituting in the previous problem. In here, we have two spares. Bring this B goes to infinity. Then you will find the answer. So that you will find is this. And the electrostatic energy can also be computed by evaluating the volume integral of electric field. And electric field is 1/2 epsilon 0. Electric field, this is the electric field that can be obtained by Coulomb law. And then volume integral can be evaluated 4 pi r squared dr. So using this, you can do this integral. As you know, the inner radius, inside the inner radius, there is no electric field. So this integral is from the radius r for the inner radius to the infinity. And that is trivial to find 1 over r. You find these two values are identical to each other. So this is what we have done with the formula Q equals CV, and this can be directly computed from the electric field squared volume integral. So these two values are equivalent. The same is true for the coaxial cable. Again, we evaluate the electrostatic energy. In the case of B goes to infinity, and the electrostatic potential energy can be computed by computing the volume integral of electric field energy. Okay, so they are identical to each other. All right. Again, repeated calculation for the finite case. In here, it is from A to B. Previous case, we extended B to infinity. There is no difference between this problem and previous one. And then we have to remember the units of the capacitance. C is not capacitor, C is Coulomb. This is farad, and you have to remember all of these useful units of SI units. And this is electrostatic coefficient constant, and in here epsilon 0 is the permittivity of the vacuum. There's some we can make use of farad to express the permittivity constant. You have to memorize this, and there are some conversion table for various useful units that is related to the capacitance. If you have taken physics course in the high school, the remaining pieces you have learned already. But in a circuit, you can connect a series of capacitors with a different capacitance. As long as the circuit is in parallel, this potential difference must be the same everywhere in the parallel connection. Parallel connection, potential difference must be the same. So this is invariant. But every capacitor has a Q equals a CV. But this each V, V1, V2, Vn, everything is the same because of this constraint of the parallel connection. Therefore, we can make use of this relation. However, as far as the charge is concerned, it is equivalent to a single capacitor connected to this battery of potential difference V. This charge Q is actually the sum of these charges. So this charge, net charge of equivalent capacitor, is the sum of every charge. Okay, we substitute in here Q equals CIV, and V is common. So I can factor V out and sum everything together. So as a result, the capacitance of the equivalent capacitor for a series of n capacitors connected in parallel connection, V is constant and C is the sum of everything. In case they are connected in series, this is a serial connection, potential should be added. So this potential is the sum of VIs. And this charge came from 0. They have been separated to Qn minus Q. And this one should also be Qn minus Q. This charge is equivalent everywhere. So using these two constraints, and the total potential is the sum of the potentials, and Q equals CV relation with this identical charge, we arrived at the formula Q equals CV gives a Q over 1 over C. As a result, we have the relation inverse of equivalence capacitance is the sum of the inverse of everything. Okay,